In this video, we discuss the traveling salesman problem, which is one of the most famous problems in combinatorial optimizations and integer programming. In the traveling salesman problem, we have a traveling salesman who must visit n cities and return to the city he started from. The traveling salesman must visit every city and it must visit each city exactly once. We are then given the cost Cij of traveling from city I to city j. The question is what is the order in which the traveling salesman should visit the cities in order to minimize the cost of his tour? Now, depending on the structure of the costs Cij, we can have many different versions of the traveling salesman problem. The most general case is the asymmetric TSP, which is when we allow Cij to be different from Cji. On the other hand, if we have a Cij equal to Cji for every I and j, for every pair of cities I and j, then we obtain the symmetric TSP. Another special case is the metric TSP, where we assume that the costs Cij satisfy the triangle inequalities Cij less than or equal to Cik plus Ckj for every three cities I, j, and k. Another very important special case of the TSP is the Euclidean TSP, and this is the case where we assume that the costs are distances in the plane. In particular, in the Euclidean TSP, instead of giving the costs, we can simply give the position of every city in the plane. In this slide, we see a very simple example of the Euclidean TSP. These black dots represent my cities, and in this case, this is an optimal solution. So in an optimal tour, the traveling salesman will travel along these segments. In particular, note that it doesn't matter which one is the city where the traveling salesman starts from. Now let's focus on the asymmetric TSP, which is really the most general type of TSP. And let's formulate it using D-graphs, also called directed graphs. A D-graph is an ordered pair D equal to VA, where V is a set of nodes and A is a set of arcs. Every arc is an ordered pair of nodes. We have an example here on the right where the nodes are 1, 2, 3, and 4. So in particular, we can visualize nodes as points or circles. And then we have 5 arcs, which are 1, 2, 3, 2, 1, 3, 3, 4, and 4, 3. So every arc is visualized by an arrow that starts at the first node in the arc and ends in the second node in the arc. Now that we have understood what are D-graphs, let's formulate the TSP. We're given a D-graph D with nodes V and arcs A, and we are given costs Ca for every arc A. The traveling salesman problem then asks us to find a minimum cost Hamiltonian cycle. So what is an Hamiltonian cycle? Well, let's start from the definition of cycle. A cycle is a sequence of arcs v1, v2, v2, v3, v3, v4, and so on and so forth until vk minus 1 vk for some integer k. In this sequence of arcs, we must have that vk is equal to v1, and that every node is traversed at most once. Now the Hamiltonian cycle is a very special type of cycle, where each node is not just traversed at most once, but exactly once. Note that, in general, a D-graph might not contain any cycle or any Hamiltonian cycle. Now that we have formulated our TSP using D-graphs, let's write an integer programming formulation. Let's start from the variables. We only need binary variables, and we need one binary variable for each arc ij. So we have xij equal to 1 if and only if the salesman goes directly from city I to city j. These binary variables allow us to write very easily our objective function, where we minimize the sum of Ca xa for every arc A. Now what about the constraints? there are several constraints in the TSP, so let's start from the easy ones. First, we definitely need to write that XA is binary for every arc A. And these are our binary constraints. Then we need to write that we leave every city exactly once. To do so, we look at every city, so every I in V, and we write that the sum of the xij is equal to 1, where j ranges over all cities such that ij is an arc. Symmetrically, we also need to write that we enter each city once. In this case, we again look at every city I, and we write that the sum of the xji is equal to 1, where j ranges over all the cities such that ji is an arc. Now, these constraints are fairly obvious, and at this point we might wonder if this formulation is valid. In other words, we're asking if the optimal cost of this integer program matches the optimal cost of the TSP problem that was defined in the previous slide. What we can do is test our formulation. So for example, we can pick an instance of our TSP and solve the integer programming formulation with some solvers and see what we obtain. Our optimal solution should correspond to an Hamiltonian cycle, so graphically something like this. However, you might find that an optimal solution instead looks like this picture here. So instead of having only one cycle, our Hamiltonian cycle, we might obtain the union of two or more cycles. And this is what often happens when you write an integer programming formulation of some problem given to you implicitly. Essentially, we forgot to write down some very important constraints. In fact, you can check that a solution that looks like this indeed satisfies all the constraints which we have written. So we need to include some new constraints that force our solution to consist of only one cycle, instead of the union of several cycles. This can be done in several ways. One way is to use the so-called Subtour elimination constraints. In these constraints, we look at every subset of nodes that is different from the empty set and different from the whole set of nodes V. The idea is that there shouldn't be any cycle or union of cycles that traverses precisely the nodes in S. This can be done by enforcing that there exists at least one arc leaving the set S. So if we define delta out of S as the set of arcs ij with I in S and j not in S, then we can write our Subtour elimination constraint as the sum of xa for every arc A in delta out of S greater than or equal to 1. At this point, if we add all the Subtour elimination constraints to the initial constraints that we defined a couple of slides ago, we indeed obtain a correct formulation of the traveling salesman problem. To prove that this formulation is indeed valid, we show a bijection between the feasible solutions of the original traveling salesman problem and the feasible solution to our integer problem. In particular, we show two things. First, that for every Hamiltonian cycle, its incidence vector x is feasible, and then we show that every feasible solution x to the integer program is the incidence vector of a Hamiltonian cycle. Okay, so let's see the proof that the Subtour formulation is correct. This is really a proof sketch, so I leave some of the details to you. First, we start with the easy direction. If x is the incident vector of a Hamiltonian cycle, then clearly all our constraints are satisfied. Let me write it. If x is the incident vector of a Hamiltonian cycle, then initial constraints and Subtour elimination constraints are satisfied. So let's focus on the harder direction. Let x satisfy the initial constraints and the Subtour elimination constraints. So the first thing we can observe is that using the initial constraints alone, we can prove that x is the incidence vector of a set of arcs that contains at least one cycle. Let's say C. I leave this step as an exercise to you, but I want to give you the key idea. You just pick any node in your graph, and due to the initial constraints, you know that there exists exactly one arc leaving it. Now let's look at the node we arrive to by traversing this arc. Once again, from the initial constraints, we know that there exists exactly one arc leaving it. And let's consider the node where we arrive to once again. At this point, this node is either a new node, different from the two previously visited, or it is one that we've already visited. Now let's say that it is a new node. Now we can continue with our argument until we find new nodes, until eventually we must visit again a node which we visited already. And this is simply because our graph has finitely many nodes. So at some point our arc must go back to some previously visited node. The question is, which node will it go back to? For example, can it go back to this node over here? No, that's not possible, because then this node would have two arcs entering it, which contradicts the initial constraints. So the only possibility is that this arc goes back to the very first node we started from. And this is how we obtain our cycle C in our claim. To conclude the proof, we only need to show that this is an Hamiltonian cycle. And here we use the Subtour elimination constraints. Then C is a Hamiltonian cycle. As otherwise, the Subtour elimination constraint corresponding to all nodes in C is violated. And this concludes our sketch of the proof of the validity of the Subtour formulation. Let's go back to the slides. Great, so now we have shown that our formulation given by the initial constraints and the Subtour elimination constraints is indeed valid. Now let's think for a minute about our Subtour elimination constraints, and in particular I want you to understand how many constraints we are writing. Well, we have one constraint for every subset of V, and so the number of constraints is essentially 2 to the cardinality of V. And this is a great drawback of the Subtour elimination constraints, since the number of constraints is exponential in the size of our D graph. Even with this great drawback, the formulation that we have just seen is the most widely used in practice. So how can you use this formulation in practice without explicitly writing down all the Subtour elimination constraints, which would require exponential time? The idea is that initially we solve the natural linear programming relaxation of the initial constraints alone, without even considering the Subtour elimination constraints. Then the Subtour elimination constraints are added only later, on the fly, when needed. As we will see in chapter 4, this is possible because the separation problem for Subtour elimination constraints can be solved efficiently. Now this discussion is very hand-wavy, but we will get back to it in chapter 4 in all details. Essentially, this approach is very similar to the cutting plane method that we discussed previously, with one key difference. Here, the inequalities that we add change the feasible region of the integer program, while in cutting plane methods, we only added cutting planes that did not change the feasible region of the integer program, but only the feasible region of the corresponding linear relaxation. Next, we see another way to eliminate cycles. So instead of Subtour elimination constraints, we can use what are called position constraints. Let's define these position constraints. Let's say that our set of nodes V is 1 until n, and then we represent by Ui the position of Cti in the Hamiltonian cycle. And note that we define Ui only for I greater than or equal to 2. Then, for every arc ij with I and j different from 1, we write the inequality constraints ui minus uj plus 1 less than or equal to n minus 1 times 1 minus xij. Now let's try to understand the idea behind the position constraints. So, when xij is equal to 0, then we obtain ui minus uj less than or equal to n minus 2. Since every u is between 2 and n, such a constraint is always satisfied. So essentially, when xij is equal to 0, then this constraint can be ignored. So it only makes sense for xij equal to 1. So what happens when xij is equal to 1? Well, in that case, we obtain that uj is greater than or equal to ui plus 1. So this tells you that along the arc ij, the u variable has to increase by at least 1. So if ui is, for example, 3, then uj must be at least 4. Okay, so now we understood a little bit better what these inequalities say, but still, what is the idea behind these position constraints? Well, the idea is the following. If your solution corresponds to an Hamiltonian cycle, then we can associate variables u to the nodes in the Hamiltonian cycle so that they keep increasing. The node right after node 1 will have the u equal to 2, then the node after will have the u variable equal to 3, and so on and so forth. At the very end of the Hamiltonian cycle, the last node will have u equal to n. So all these position constraints are satisfied along the Hamiltonian cycle. And this really works because we have constraints corresponding to all arcs that don't touch the node 1. Now let's see instead what happens if you have a feasible solution corresponding to the union of 2 or more cycles. Well, in that case, at least one of the 2 cycles will not contain node 1. Therefore, you will have a position constraint corresponding to every arc in the cycle. Now, along the cycle, the u variables must always increase due to these constraints. But of course that's not possible because this is a cycle. At some point you will be back to a previously considered node, and so the u variable must decrease back again. Now let's use this understanding to prove that the formulation given by the initial constraints and the position constraints is indeed valid. To do so, we need to prove the following 2 statements. First, that for every Hamiltonian cycle C, there exists a feasible solution xu to our integer program, where x is the incidence vector of C. Vice versa, we need to show that for every feasible solution xu to our integer program, x is the incidence vector of a Hamiltonian cycle. We are now ready to show that the position formulation is correct. Let's start from a Hamiltonian cycle. So let x be the incidence vector of a Hamiltonian cycle. Then the initial constraints are satisfied. This is trivial. Now what is less trivial is to show that also the position constraints are satisfied. To do so, we use the same type of intuition that we discussed when we defined the position inequalities. So we define UI to be the position of node I greater than or equal to 2 in the Hamiltonian cycle. We show that with this choice of UI, then the position constraints are satisfied. Two cases, xij equal to 1 and xij equal to 0. So, if xij is equal to 1, then the left-hand side of the inequality is ui minus ui plus 1 plus 1, and the right-hand side is equal to 0. So, the inequalities are satisfied. Instead, in the case xij equal to 0, our left-hand side is equal to ui minus uj plus 1, which is less than or equal to n minus 1, while the right-hand side is equal to n minus 1. So also in this case, the inequalities are satisfied. And this concludes the first half of the proof. Let's focus now on the opposite implication. Conversely, let xu satisfy initial constraints and position constraints. Now, of course, if x is the incidence vector of a Hamiltonian cycle, we are done. So let's assume that it is not. So otherwise, we know that the initial constraints implies that x is the incidence vector of a set of arcs that contain a cycle, capital C, not containing node 1. This is because, since we don't have an Hamiltonian cycle, then x corresponds to more than one cycles, and so at least one of them will not contain node 1. Now, summing the position constraints for every ij in the cycle C gives the inequality cardinality of C less than or equal to 0. And you should check that. And this gives us a contradiction. Why is this a contradiction? This is because C is a cycle and it contains at least 2 nodes. And this concludes our proof of the validity of the position formulation. So now let's get back to the slides. At this point, we have obtained 2 different formulations of the traveling salesman problem. Both use our initial constraints, and then one uses the Subtour elimination constraints, while the second one uses the position constraints. So we can now ask how these 2 formulations compare. Our first idea is to use our concept of better formulation. However, it's not really directly applicable to this setting. The reason is that our 2 formulations here live in different spaces. Both of them have variables xij for every arc ij, but our second formulation, the one that uses the position constraints, also has the additional variables ui. Therefore, if we look at the 2 corresponding natural linear relaxations, they live in different spaces, and so we cannot ask whether one polyhedron is contained in the other one. Actually, this concept of better formulation can still be applied in this setting, but it involves a projection step, which essentially gets rid of the U variables, but we're not going to discuss now this approach. So what we can say for now is that the formulation based on the Subtour constraints has fewer variables. In particular, it has n square variables as opposed to the n square plus n of the formulation based on the position constraints. But on the other hand, the formulation based on the Subtour constraints has many more inequalities. We saw that the number of Subtour elimination constraints is 2 to the n, while the number of position constraints is only n square, because we have one inequality for every arc. From a practical perspective, the formulation based on Subtour constraints gives better bounds for branch and cut. And this is why, among the two formulations, it is the one that is most used in practice, even though it is harder to use because it requires some kind of cutting plane method in order to deal with this large number of inequalities. Now I want to talk about the symmetric TSP. This is a very special case of the traveling salesman problem, and it is a very nice setting that will be useful also for examples later on in the course. A great thing about the symmetric TSP is that we can use graphs rather than d-graphs. Essentially, graphs are like d-graphs, but where arcs are unordered pair of nodes rather than ordered pair of nodes. Due to this difference, in graphs we have edges rather than arcs. In the symmetric TSP, we're then given a graph G with node set V and edge set E, and we're given costs CE for every edge E. In the symmetric TSP, our goal is to find a minimum cost Hamiltonian cycle. However, our definition of Hamiltonian cycle is slightly different, because now we're talking about graphs instead of d-graphs. So in a graph, a cycle is now a sequence of edges, v1, v2, v2, v3, v3, v4 until vk minus 1 vk. We must have that vk is equal to v1 and every node is traversed at most once. So it really is the same definition as the definition of cycles for d-graphs, but here we have edges rather than arcs. Similarly, a Hamiltonian cycle in a graph is a cycle that goes through each node exactly once. Now we can write the Dantzig-Fulkerson-Johnson formulation for the symmetric TSP. The idea is very similar to the idea that allowed us to define the formulation for the asymmetric TSP based on Subtour elimination constraints. But of course, since here we have edges rather than arcs, there are a few differences. Our objective function is what you would expect, is a sum of CE XE for every edge E. Once again, we have that XE is supposed to be in 0, 1 for every edge E. Now let's consider the degree constraints, which correspond to our initial constraints in the case of a d-graph. For a d-graph, these constraints used to say that we must leave every node precisely once and that we must enter every node precisely once. However, here there's no notion of entering or leaving. So what we write instead is that for every node I, there are precisely 2 edges in the tour touching it. We can write this as the sum of the XE for every E in delta of I equal to 2, where delta of I is defined as the set of edges that contain node I. Then we need our Subtour elimination constraints. The ones for d-graph used to say that there must be at least one arc leaving every subset of nodes S. Again, here we cannot specify who enters and who leaves, so in total we will have at least 2 edges that go from S to outside of S. And you can think of them as one leaving and one entering the set S. If we define delta of S to be the set of edges with precisely one node in S and one outside of S, then we can write these inequalities as the sum of XE for E in delta of S greater than or equal to 2. I leave as an exercise for you to show that this formulation is indeed valid for the symmetric traveling salesman problem. Similarly to our formulation for the asymmetric TSP, also this formulation is very effective in practice despite its exponential number of constraints. To conclude this video, I just give you a little bit more information about the traveling salesman problem. If you're interested in this beautiful problem, I refer you to this website over here, which is maintained by William Cook, who is one of the leading experts in TSP. You can find in the App Store is Concord TSP app, which solves TSP problems extremely effectively, leveraging on decades of studies on the TSP. The research done in the past decades allowed to solve very large instances of the TSP, even with 85,000 cities. This is really impressive if you consider that the corresponding integer program has 3.5 billion binary variables. I encourage you to play with this beautiful app, and with this we conclude our video on the traveling salesman problem.